In these videos, we will address one of the most strategic topics in the development of large-scale photovoltaic plants, the advanced integration of energy storage systems, BESS, in hybrid utility-scale configurations. The objective of these videos is to offer a comprehensive engineering overview, covering everything from electrical and thermomechanical design to optimized operation, lifecycle management, and the implementation of artificial intelligence to maximize the system's technical and economic performance. The focus is on BESS systems, not as a simple complement, but as a fundamental pillar for enabling new functionalities in photovoltaic plants, such as smart storage, controlled dispatch, ancillary grid services, and resilience and firm capacity in PPAs. Integration with solar plants requires advanced engineering, where the following converge: electrical power, dynamic control, thermal modeling, and international regulations. And of course, artificial intelligence and digital twins. This content is updated as of May 2025 and includes the latest advances in modular design, predictive control algorithms, synchronization protocols, and LCOE optimization strategies. In the following videos, we will analyze technical design, safety, validation, and operation criteria, all with a practical approach directly applicable to projects over 50 MEGP. We now move on to the first block: integrated electrical design criteria for PV plus BESS systems. Let's start with the technical heart of any BESS plus photovoltaic integration: the integrated electrical design of the system. This phase defines the efficiency, component compatibility, and scalability of the project. Here, we see the three typical configurations: AC coupling, alternating current connection with efficiencies between 96% and 97%. It is ideal for retrofitting or when maintaining a degree of independence between the PV and BESS systems is desired. DC coupling, direct current connection with efficiencies of 98% and 99%. This type allows for shared inverters, reducing CAPEX, and optimizing joint control. Highly recommended for new integrated plants. Hybrid combines both connections, allowing for dynamic optimization. It is useful in plants with complex energy flows or multi-service systems. Choosing the right topology directly impacts overall efficiency, modularity, and operating costs. Inverters are key to hybrid system performance. We must consider bidirectionality, efficiency greater than 98%, and the ability to actively control PQ power are required. Hybrid inverters. They allow dynamic DC-DC control and adapt to different BESS-PV ratios, from 0.25 to 1 to 1 to 1. Grid forming capability, especially important for black start or microgrids. Controllability. Ramps under 500 milliseconds and response in less than 20 milliseconds to provide grid auxiliary services. In DC-coupled systems, transformers must be designed according to specific criteria. Optimal ratios. We recommend oversizing by 10 to 15% to avoid harmonic distortions. Losses. Keep them below 0.8% under load and less than 0.1% under nominal load. Protections. Include residual DC current detection systems. Cooling. In projects larger than 30 megawatts, it is recommended to use transformers with CAN or CANAF cooling. Finally, we look at the energy control between PV, BESS, and inverter, which should allow for real-time active and reactive regulation. Advanced strategies, such as peak shaving and ramp rate control. Grid synchronization, using adaptive PLL in less than 20 milliseconds. Open protocols. IEC 618500, REST API, and OPC UA to facilitate interoperability and connection to SCADA. This block is key to integrating the BESS as an operational asset within the electrical system and not as a simple connected battery. Once the electrical layout has been defined, the next critical step is the technical and modular sizing of the BESS system, based on the project's energy objectives. Each application requires a different optimal ratio between BESS capacity and installed photovoltaic power. Energy shifting, shifting solar generation to peak hours. Recommended ratio between 1.2 and 1. 3. Frequency regulation, between 1.5 and 1. 8. Firm capacity for PPAs, from 1 to 1 to 2 to 1. Spinning reserve, grid services, from 1 to 4 to 1 to 6. As we can see in the graph, the most demanding application for peak megawatt storage is firm capacity, as it requires long-term autonomy to ensure contractual delivery. The system architecture also determines the maintenance, redundancy, and deployment strategy. We distinguish 3 levels. Rack, 50 to 250 kilowatt hours. Minimum functional unit, easy to replace. Container, 1 to 5 megawatt hours. Standard modular unit, ideal for progressive scaling. Block, 10 to 100 megawatt hours. High density, designed for plants larger than 100 megawatts. Key features. Advantages: selective maintenance, N+1 redundancy, ease of integration. Limits: higher BOP per unit, greater control complexity without advanced monitoring. MTTR, mean time to repair, 1 to 4 hours in a rack versus 24 to 72 hours for a non-modular system. Technical availability: greater than 99.5% with redundant design. In another graph, we see how CAPEX and technical complexity evolve as scale increases. Beginning at 200 megawatt hours, complexity increases dramatically, moving to a level greater than 7 out of 10, due to substation limitations, more than 150 kilovolts, coordination of more than 50 inverters. Distributed control across multiple containers. A reduction in CAPEX is observed with size, but also an increase in integration and synchronization challenges. Some technical and economic limiting factors may include maximum installed density, 2 to 3 megawatt hours per 100 square meters. Requires specific structural design, NFPAs, thermal loads, safety, precise synchronization with multiple inverters, latency less than 100 milliseconds, BOS, balance of system. Economies of scale are maximized up to 200 megawatt hours. Thereafter, a diminishing return curve. Infrastructure threshold, greater than 500 megawatt hours, requires dedicated civil engineering and dedicated substations.
Hemos visto cómo elegir correctamente el ratio BESS-PUV y la arquitectura del sistema permite lograr un equilibrio entre rendimiento, mantenimiento y escalabilidad.
Once the electrical and modular configuration of the BESS system has been defined, it is time to address one of the most critical aspects for long-term operational reliability: the thermal and structural management of the storage system. The thermal system of a modern BESS must be managed hierarchically. Cell level: thermal homogeneity of less than plus or minus 2 degrees between cells must be maintained to avoid degradation imbalances. Module level: crossflows and phase change materials, PCM, are applied to efficiently dissipate heat in high-density environments. System level: predictive control with look-ahead logic and N+1 redundant design is used in pumps and coolers. Thermal simulation: use of coupled electrothermal models to validate behavior under dynamic loading and long cycles. This multi-level design allows thermal failures to be predicted, climate consumption to be optimized, and cell lifespans to be extended by up to 20%. Let S now analyze the 3 heat flow configurations: longitudinal, flow parallel to the cells; efficiency, between 75 and 82%. Transverse, crossflow; efficiency, between 83 and 88%. Vertical, flow from bottom to top; efficiency, between 80 and 85%. And depending on the medium, air, low cost, low efficiency. Hybrid, compromise between efficiency and cost. Liquid, high thermal efficiency and energy density, but with higher implementation costs. In hot climates or projects with high densities, greater than 200 watt-hours/liter, the liquid system is essential to prevent accelerated degradation. The use of computational fluid dynamics, CFD, has revolutionized thermal design. Critical zones: thermal differences of up to more than 15 degrees are detected between modules during peak operation. Semi-open environments. Natural flows are simulated in non-hermetic cabinets. Critical points. Hotspots are identified using IR sensors. Practical result: A 32% reduction in HVAC system consumption is achieved by optimizing air paths alone. Mechanical integration must consider loads, vibrations, and seismic conditions. Foundations. Reinforce slabs with a capacity greater than 3,000 kilograms per square meter to support high-density modules. Weight. Between 20 and 30 tons per MWH, depending on the technology, and cooling. Seismic anchors. Required if the module exceeds 0.3 grams of acceleration. Seismic zones such as Chile, Japan, and Eastern Andalusia. Vibrations. Impacts at the cell level of less than 0.5 grams must be damped to avoid internal microfractures. As we've seen, poor thermal and structural design compromises system safety, efficiency, and lifespan. Therefore, in the following video, we'll discuss how these factors directly impact battery life cycles and electrochemical degradation.